One of the reactions that we've looked at pretty extensively in this chapter is nitration. And this is kind of interesting because we haven't learned what to do with that nitro group once it's on the benzene ring. We've learned that it can deactivate the ring. We've learned that it can direct further substitution into the meta position. But we don't really know what to do with that nitro group once we have it on the ring. And as organic chemists, often we're interested in synthesis and being able to change one functional group into a different functional group. So in this video, we're going to learn what to do with those nitro groups. And the reaction we're going to focus on in this chapter is the reduction of the nitro group to the amine. Now, in order to carry this out, we're going to take hydrogen atmosphere, catalytic palladium metal, in this case it's palladium on carbon, and then we're going to do this reaction in an ethanol, or usually a protic solvent. Now it's important to point out, whenever we do this reaction, right, we're starting with an electron-poor ring. That nitro group is a meta-director. And when that reaction is completed, now we have an electron-rich ring, and that nitrogen becomes an ortho-para-director, right? So we're completely changing the reactivity of this benzene system. And sometimes we can use that to our advantage, right? Or at least it's something that we have to think about when we are planning syntheses with amine groups in them on a benzene ring. Now, once we've made this amine, we have to think about what we can do with it. What other reactions do we know that involve amines? Well, one of the reactions that we know is Amine formation. Right? And in amine formation, we would take an amine, a primary amine, and add that to a ketone or an aldehyde. Right? We can also do enamine formation. Right? And remember, enamines form from the addition of secondary amines to aldehydes and ketones. Right? Using both of these, we can carry out reductive amination. Through the reduction of an iminium intermediate, right? And another reaction we've learned that involves amines is amide formation. Right? Or the addition of an amine to a carboxylic acid derivative. One of the reactions that we're going to look at in the next chapter, and one that I'll introduce here, is we can take this amine and treat it with sodium nitrite, NaNO2, and a strong acid, in this case HCl, and we would make a diazonium salt. Diazonium, in this case, refers to two nitrogens. The onium suffix indicates that this is a positively charged ion, and in this case the chloride is going to be the negative anion. Right, so this diazonium salt is actually really useful, but the one thing that we're going to look at right here is if we just treat this with water, this is going to give us a way to make phenols. Right? And that occurs basically through the displacement of molecular nitrogen. Right? So this is an important reaction. This is a reaction, like I said, we're going to learn in the next chapter. But it's one thing that we can do with amines to further functionalize them, right? Make these diazonium salts, and then we can add really any number of nucleophiles to displace that diazonium salt. All right, so here are several reactions that we can do with amines, just as a reminder, right? All of these reactions should be on your functional group sheet. What I want to look at is how we're going to take advantage of this nitro group to amine reduction to maybe make two different regioisomers of a compound. And so the two regioisomers that we're going to look at are going to both be amines, and both are going to have bromine atoms on them. right? And I want to think about how we're going to make these, right? What are the steps that we have to go through to make these two regioisomers? Right, so if you want to, pause the video now and see if you can come up with a synthesis for both of these regioisomers that would start from nitrobenzene. All right, maybe take 5-10 minutes, as much time as you need, all right, to come up with a synthesis, and then restart the video, and then we will go back over this synthesis. All right, so I want to first take a look at one pathway, the para-bromo amine, right? And we're going to kind of break this down into two parts. We're first going to focus on how we're setting up the relationship between the nitrogen atom and the bromine. And in the second part, we're going to look at how we get this 5-membered alkyl group onto nitrogen, because obviously that can't take place through reduction. All right, so the first step of this synthesis in one direction is going to be direct reduction of that nitro group. So if we reduce it using hydrogen and palladium on carbon, we would form the aniline compound. Right? And then in order to get a bromine in the para position, remember we can't just treat this with bromine, but we need to reduce the reactivity of that amine. If we would treat this aniline with bromine, we would get bromination in both the ortho positions and the para position. So we first have to acetylate the nitrogen, right, with acetic anhydride. And now this acetyl group is removing some of the electron density from the ring, right? Because now the lone pair and nitrogen have to, those electrons are kind of sharing resonance into the carbonyl and also into the ring. So once we have that acetyl group on there, we can treat with bromine, molecular bromine, acetic acid, and that installs the bromine in the para position as the major product. Right, and then we can deprotect using acid and water. And that gives us the para-bromoaniline. All right, so you can see we just set up the para relationship between the nitrogen and the bromine, just like we did there, okay? If we want to make the metabromoaniline, what we would do is, rather than reducing first, we would start out with a bromination. And in this bromination, I'm going to introduce a different Lewis acid. So we've been using aluminum trichloride. Iron tribromide is another common Lewis acid that you can use for electrophilic bromination of a benzene ring. Right? When we do this bromination, we would expect only one bromine to go on. And it would be added to the meta position relative to the nitro group. Once we have that bromine in position, then we can reduce the nitro group down to the amine with hydrogen on palladium. All right, and so now we have our second compound almost, right? And you can see that we set the relationship between the nitrogen and the bromine, just like we have up here, okay? Now, the second part of the synthesis is going to be installing this 4-carbon alkyl group onto the nitrogen. And the way that we're going to do that is we're going to take a dialdehyde, a 4-carbon dialdehyde. So 1, 2, 3, 4. The amine and sodium cyanoborohydride. Right, so this is going to be a reductive amination. The amine is going to add to one aldehyde group, and we're going to reduce that iminium ion that forms, and then the resulting secondary amine will add to the other aldehyde group. We'll do another reductive amination, and that should give us our 5-membered ring. Do the same thing here. And then just to represent both of these compounds, what I will do is I will draw the nitrogen with the 5-membered ring, and then I'm just going to draw the bromine substitution through the middle, just to show that we're getting this reaction to go on both of these substrates, and then this product represents the product that we would get from the meta-bromoamine and the para-bromoamine. Right, so this is a good overview of how we can use these nitro groups for synthetic purposes. What I want you to do, so everybody should have sent me a video detailing the Wolff-Kishner reduction. What I want you to do, again, just to check for my purposes to see that you're watching a video, what I want you to do is show me the mechanism of this reaction. All right, taking the amine and making the diazonium chloride using sodium nitrite and hydrochloric acid. Right, so draw out that mechanism, take a picture of it, and send me that picture in an email, just so I know that you're following along with these videos.